By 1964, the United States already possessed what many believed was the ultimate reconnaissance aircraft. The Oxcart program, better known to the public as the SR-71 Blackbird, had redefined what was possible in aerial intelligence. Flying at speeds exceeding Mach 3 and at altitudes above 80,000 feet, it could outrun missiles, evade interceptors, and vanish before radar operators fully understood what they were tracking. For a brief moment, the CIA believed it had achieved total dominance of the skies. But inside the agency's Directorate of Science and Technology, there was no sense of victory, only urgency, because intelligence, by its nature, is temporary. Soviet radar systems were improving. Surface-to-air missile technology was advancing at an alarming rate. Tracking systems were no longer reactive, they were becoming predictive. The margin of safety that once protected American reconnaissance missions was beginning to erode. The Blackbird was still unmatched, but it would not remain that way forever. The agency reached a quiet but critical conclusion. If they wanted to remain invisible, they could no longer rely on speed alone. They would have to operate beyond the limits of conventional aviation. They would have to move into the edge of space. What followed was not an incremental upgrade, it was a complete departure from everything that had come before. A program so radical that even within the CIA, access was tightly restricted. A project that would push both engineering and human endurance to their absolute limits. They called it Project Isinglass. The name itself was deliberately unremarkable, taken from a substance used in brewing to clarify liquids. But within classified documents, the meaning was clear. This was a system designed to clarify the Soviet Union from above, at speeds and altitudes where interception would become physically impossible. The objective was simple to state and nearly impossible to achieve. Mach 20. At that velocity, the aircraft would not simply outrun threats, it would exist in a domain where threats could not function. But achieving that speed required abandoning the idea of traditional aircraft altogether. Isinglass was never intended to take off from a runway. Instead, it would begin its mission attached to a larger carrier aircraft, most likely a modified B-52 bomber. The concept was precise. The carrier would climb to high altitude, release the isinglass vehicle, and then clear the area before ignition. Seconds later, the mission would truly begin. The onboard rocket engines would fire, pushing the vehicle into a steep ascent toward the upper atmosphere. The acceleration would be immediate and violent. Within minutes, the pilot would be propelled beyond the altitude of conventional aircraft, approaching a suborbital trajectory. From there, isinglass would transition into what engineers described as a boost glide phase. Rather than flying through the atmosphere in the traditional sense, the vehicle would skip along its upper boundary. Each contact with the thin atmospheric layer would generate lift, allowing the aircraft to maintain hypersonic speeds while gradually covering vast distances across the Earth's surface. According to internal CIA memoranda, this trajectory would allow the vehicle to remain above the effective ceiling of both existing and projected Soviet interceptors. In simple terms, it would be untouchable. At least that was the theory, because in practice, every aspect of the design pushed the limits of known science. The structure of the aircraft alone presented a challenge unlike anything faced in previous aviation programs. At Mach 20, friction with even the thin upper atmosphere would generate extreme heat. Temperatures along the leading edges of the wings were expected to exceed 3,000 degrees Fahrenheit. At those levels, conventional materials would fail almost instantly. Even titanium, which formed the backbone of the SR-71, would not survive prolonged exposure. Engineers turned instead to a nickel-based superalloy known as Re-41. This material, originally developed for high-temperature applications, offered the strength and thermal resistance required for hypersonic flight. But even Re-41 had limits, and those limits would be tested continuously. The reality was unavoidable. Isinglass was not just an aircraft, it was a machine operating on the edge of structural failure. One engineering log described it in blunt terms. A system in which thermal management was not a feature, but the primary constraint. The aircraft was, in effect, a controlled furnace moving at 20 times the speed of sound, and inside that furnace would be a pilot. This is where the mission profile becomes more difficult to ignore, because the men selected for Isinglass were not being prepared for a standard reconnaissance role. They were being prepared for something far more uncertain, something that, even by the standards of Cold War aviation, bordered on experimental spaceflight. Historical analysis suggested that the CIA was quietly targeting pilots with experience in extreme flight regimes, particularly those associated with high-altitude rocket aircraft programs. These were individuals already accustomed to operating at the boundary between atmosphere and space, but even among that group, information was tightly controlled. Pilots were not given a complete picture of the system they were expected to operate. They couldn't be. At Mach 20, the environment itself introduced variables that were not fully understood. One of the most significant challenges was the formation of a plasma sheath around the vehicle. As the aircraft moved at hypersonic speed, the air surrounding it would ionize, creating a layer of superheated plasma. This phenomenon had immediate and serious consequences. First, it subjected the airframe to extreme thermal stress, pushing materials to their limits. Second, it created a communications blackout. Radio signals could not penetrate the plasma field. Once the vehicle reached peak velocity, all contact with ground control would be lost. The pilot would effectively disappear from radar and communication systems, operating in complete isolation for the duration of the high-speed phase. From the outside, the aircraft would simply vanish. From the inside, the pilot would be alone. Mission parameters had to be pre-programmed. Navigation systems had to function without real-time correction. Every stage of the flight depended on systems that could not be adjusted once the vehicle entered its hypersonic regime. This level of isolation introduced a new kind of risk, because it meant that even if something went wrong, there would be no immediate response, no instructions from the ground, no external intervention. Only the pilot and the machine. To adjust the thermal problem, engineers proposed a solution that was both innovative and deeply complex. Liquid hydrogen would be circulated through channels within the aircraft's skin. As it flowed, it would absorb heat generated by atmospheric friction, preventing the structure from melting. The heated hydrogen would then be redirected into the rocket engines as fuel, a closed-loop system, efficient in theory, necessary in practice, but also unforgiving. Any failure in the cooling system would lead to a rapid and catastrophic temperature increase. At Mach 20, there would be no margin for error. The aircraft would not gradually fail. It would be destroyed in seconds. The propulsion system itself represented another leap into the unknown. The Pratt & Whitney XLR-129 rocket engine was designed to deliver immense thrust using a staged combustion cycle. It was an ambitious design, pushing the boundaries of what was achievable with existing technology. Though the engine would never see operational use in isinglass, its development would influence later advancements in rocket propulsion, including systems used in spaceflight programs. At the time, however, it remained experimental, unproven and critical to the success of the mission. Everything about isinglass existed at the edge of feasibility. The structure, the propulsion, the thermal systems, all of it required precision at a level rarely achieved in operational aircraft. And still, the mission demanded more, because speed and altitude alone were not enough. The purpose of isinglass was reconnaissance, to observe, to record, and to deliver intelligence that could not be obtained by any other means. To accomplish this, the aircraft was equipped with a specialized optical system designed to function under extreme conditions. At hypersonic speed, the plasma sheath surrounding the vehicle would distort incoming light, making traditional imaging systems ineffective. Engineers developed a solution involving a series of mirrors and corrective optics designed to compensate for those distortions. The goal was precise: capture high-res images from approximately 100 miles above the Earth, with clarity sufficient to identify objects less than a foot in size. From that altitude, and at that speed, the aircraft would not simply observe the Soviet Union, it would map it in detail, and it would do so without warning. But as with every aspect of the program, the deeper one looks, the more questions begin to emerge. Because within the design documents, there are indications that isinglass may have been intended for more than reconnaissance. Subtle details in the internal configuration suggest the presence of a payload bay, small but functional, enough to carry something beyond cameras. Enough to raise the possibility that the aircraft could have been adapted for a secondary role, a more direct role. Some analysts have speculated that the CIA explored the concept of a precision strike variant, a system capable of delivering a payload anywhere on Earth in under 30 minutes, bypassing traditional defense systems entirely. If true, this would have transformed isinglass from a passive observer into an active strategic platform. But like many elements of the program, confirmation remains hidden behind layers of redacted documentation. What is clear is that the risks associated with isinglass were unlike anything seen before. An internal review conducted in 1967 estimated the cost of a small operational fleet at over $2.6 billion. The technical risk was categorized as extreme. Loss projections suggested that one aircraft could be lost for every 10 missions. Those numbers alone were enough to raise serious concerns, because behind every aircraft was a pilot, and unlike the machines, the pilots were not replaceable. Yet the missions continued to be studied, refined, and prepared, because from the CIA's perspective, the potential reward outweighed even those risks. The ability to see anything, anywhere, without interception, it was an advantage too significant to ignore, even if the people tasked with achieving it were only ever told half the story. By 1967, Project Isinglass had moved beyond theory and into something more dangerous. Feasibility studies had been completed, wind tunnel data had been analyzed, materials had been selected, tested, and in some cases pushed to failure. The program had reached a point where the remaining questions were no longer conceptual, they were existential. Could a human survive inside a vehicle traveling at Mach 20? And if something went wrong, what would be left to recover? Internal documents from this phase revealed an increasing focus on survivability of the pilot. Engineers were no longer just solving aerodynamic problems, they were confronting the biological limits of the human body under extreme conditions. At hypersonic speeds, heat was only part of the equation. The formation of the plasma sheath, already identified as a communications barrier, introduced additional complications. It interfered not just with radio signals, but with sensor accuracy and optical clarity. Even the advanced mirror-based imaging system required constant recalibration to compensate for distortion. But the deeper issue was isolation. Once the vehicle entered its high-speed glide phase, the pilot would effectively vanish from all external systems. No radar lock, no voice communication, no telemetry that could be reliably interpreted in real time. From the perspective of mission control, the aircraft would become a ghost, and from the perspective of the pilot, the mission would become a one-way commitment. There are strong indications that the CIA understood this clearly. A partially declassified internal review from 1967 categorized the technical risk of the program as extreme, but that label only begins to describe the reality, because buried within the same review were projections that painted a far more sobering picture: a loss rate of 1 aircraft for every 10 sorties. 10 missions, 1 loss. In conventional aviation, such numbers would be unacceptable. In Project Isinglass, they were considered manageable. This is where the secrecy surrounding the program becomes more than just procedural. It becomes personal, because the pilots selected for these missions were not being briefed in the way traditional military aviators were. They were given mission parameters, system overviews, and operational expectations, but always within carefully controlled limits. Compartmentalization was absolute. No single individual, outside of a small group within the agency, had access to the complete picture. Pilots knew they were testing something unprecedented. They understood the risks were high, but the full extent of those risks remained obscured, and nowhere is that more evident than in the redacted sections of the program's final reports. Among the most heavily censored portions of the Isinglass documentation is a section labeled Annex, Recovery and Re-entry. Entire pages have been blacked out, leaving only fragmentary headings and partial sentences visible. This has led to significant speculation among historians and aerospace analysts, because the obvious question remains unanswered. If something went wrong at Mach 20, how did the pilot escape? The likely answer is the one the documents do not explicitly state. At those velocities, traditional ejection systems become useless. The forces acting on the aircraft, combined with the extreme temperatures and aerodynamic stresses, would make controlled escape virtually impossible. Any catastrophic failure would occur too quickly. There would be no time to react, no opportunity to deploy emergency systems, no realistic chance of survival, and yet the missions were still being planned, which raises a more unsettling possibility. Thermal management remained the central problem. While the liquid hydrogen cooling system showed promise in theory, maintaining structural integrity across repeated missions introduced new complications. Microfractures, material fatigue, and cumulative heat damage all threatened to reduce the lifespan of the aircraft. Each flight would push the vehicle closer to its limits, and those limits were not fully understood. Programs such as Corona and later KH-9 were demonstrating that high-resolution imagery could be obtained from orbit without risking human pilots. These systems operated continuously, passing over targets with predictable frequency, and most importantly, did not require a pilot to survive extreme conditions. By 1968, the decision became inevitable. Project Isinglass was officially cancelled. The stated reasons were straightforward. The cost of developing and maintaining the system was too high. The technical risks remained unresolved, and the rapid advancement of satellite technology had rendered the core mission increasingly redundant. Ultimately, Project Isinglass represents a moment in history where the pursuit of intelligence pushed beyond the boundaries of practicality and into the realm of pure ambition. A time when the CIA believed that no speed was too fast, no altitude too high, and no risk too great. They understood the importance, but the full story remained just out of reach.